In this video, I'm going to share on chemical equilibrium. First, we are going to look at what is reversible and non-reversible reaction. Second, we are going to look at the characteristic of dynamic equilibrium. Third, we are going to look at the law of mass action and how to write equilibrium constant expression in terms of concentration and partial pressure. And fourth, we are going to look at what are homogeneous and heterogeneous equilibria. And the last part of this video, I'm going to explain 3 different ways for a reversible reaction to reach equilibrium using graph. Hey, I'm Teacher Tan. If you like my video, do remember to click on the subscribe button below so that you won't miss any notification as I update my channel. Why a chemical equilibrium is a dynamic equilibrium? To understand this, first you must understand a few terms. The first term is non-reversible reaction. Non-reversible reaction are the reactions that can only proceed in one direction, and the reactions will stop when a reactant is completely used up to form products. These are examples of non-reversible reaction. For non-reversible reaction, the arrow in the chemical equations is pointing in one direction only. Reversible reactions refer to reactions that can occur in both directions, forward and backward directions. And these are the examples of reactions that are reversible. You can see that for reversible reactions, the arrows are pointing forward and backward directions. In a reversible reaction, initially the reactions proceed towards the formations of products. As soon as some product molecules are formed, the reverse process begins to take place, and reactants molecules can also be formed from the product molecules. For example, for a reversible reaction whereby reactant A is converted to product B. Initially, the concentrations of reactant A decreases with time. As the concentrations of reactants A decrease, concentrations of products will increase with time as more product B is formed from the reactant A. After time t, the concentrations of A and B remain unchanged or constant, and at this stage, the system is said to be at equilibrium state. The equilibrium achieved is a dynamic equilibrium. What does that mean? Basically, it means that after the time t, when the reactions has achieved equilibrium, the reaction did not stop, but the rate of forward reactions whereby A is converted to B is equal to the rate of reverse reactions whereby B is converted to A. As the rate of forward reaction A converted to B is equal to the rate of reverse reaction B converted to A, then the concentrations of A and B will remain constant at equilibrium. You must take note that for dynamic equilibrium to occur, the system must be in a closed system. What is law of mass action? Law of mass action expresses the relationship between reactants and products at equilibrium in terms of concentration or partial pressure. So what's the relationship between reactants and product at equilibrium? When an equilibrium is reached, a constant K can be expressed as the ratio of product to reactant in terms of concentration or partial pressure. For example, in this reaction, with A mole of A reacts with B moles of B to produce D mole of D and E moles of E. When equilibrium is reached, a constant, what we call as equilibrium constant K, can be written as the ratio of the multiplications of the concentrations of product D, which raised to the power of D, with concentrations of product E, which raised to the power of E, to the multiplications of the concentrations of reactant A, raised to the power of A, with the concentrations of B, raised to the power of B. When the equilibrium constant K is right in terms of concentration, then the symbol K will have the subscript C to represent concentration, and the square bracket used is to represent the concentrations of each reactant and product. For equilibrium constant K, it can also be expressed in terms of partial pressure if reactants and products are in the gaseous state. K value does not change with the change in concentration, pressure, or with the presence of catalyst. What is equilibrium constant K? Basically, equilibrium constant K tells us how far does a reaction proceed towards product at a given temperature. Larger equilibrium constant K value means that at equilibrium, there are higher concentrations of products than reactants, and the equilibrium positions lies more to the right. For example, at equilibrium, this reaction has the equilibrium constant K value of 2.2 times 10 to the power of 22. Large K value means that at equilibrium, there are higher concentrations of product carbon dioxide than the concentrations of reactant carbon monoxide and oxygen. While small K value means that the equilibrium positions lies to the left. Higher concentrations of reactants than products when the equilibrium is reached. For example, for these reactions at equilibrium, the K value is 1 times 10 to the power of negative 30. So means that at equilibrium, there are higher concentrations of reactant nitrogen gas and oxygen gas than the concentrations of product nitrogen monoxide. There are two types of equilibria, homogeneous equilibria and heterogeneous equilibria. Homogeneous equilibria refer to the equilibrium with reactions in which all the substances, reactants and products having the same phase. Example, N2O4 in the gaseous state and the product 2 moles of nitrogen dioxide is also in the gaseous state. Haber process, nitrogen gas react with hydrogen gas to give the ammonia also in the gaseous state. Since all the reactants and the products are of the same phase, they are considered as homogeneous equilibria. For heterogeneous equilibria, basically it refers to the equilibrium with reactions in which substances have 2 or more phases. For example, we have ammonium hydrogen sulfide in a solid state, but the product, ammonia gas and hydrogen sulfide in the gaseous state. So there are 2 different phases. So this equilibrium is therefore heterogeneous equilibrium. And the second example is potassium nitrate. Dissociate to become potassium nitric solid and oxygen gas. So in this equilibrium, also having 2 phases, hence this equilibrium is considered as heterogeneous equilibrium. How to write the equilibrium constant for homogeneous equilibria? In the first examples here, we have the homogeneous equilibrium in the gaseous state. Both the reactants and the products are in the gaseous state. So when we have gaseous state equilibrium, then we can write the equilibrium constant in terms of concentrations and partial pressure. So how to write the equilibrium constant? Must remember it is the ratio of the product to the reactant. Hence, to write the equilibrium constant in terms of concentration for this reaction would be the concentrations of the product nitrogen dioxide raised to the power of 2, which is consistent with the coefficients in the balance equation, to the concentrations of the reactant dinitrogen tetroxide. Besides the equilibrium constant in terms of concentration, because the system are in the gaseous state, we can also write the equilibrium constant in terms of partial pressure. Again, to write equilibrium constant, it is the ratio of product to the reactant. So to write the equilibrium constant in terms of partial pressure, Kp, we can write Kp equals to partial pressure of the product nitrogen dioxide raised to the power of 2, same with the coefficients in the balanced chemical equation, to the partial pressure of the reactant dinitrogen tetroxide. For the homogeneous equilibria in the aqueous state, we only can write the equilibrium constant in terms of concentration. So the equilibrium constant in terms of concentrations Kc can therefore be written as the concentrations of the product hydrogen ion multiplied with the concentrations of fluoride ion to the concentrations of the reactant hydrogen fluoride. How to write the equilibrium constant expressions term for heterogeneous equilibria? So must remember the way to write it is still the same. It is a ratio of product to reactant. But for heterogeneous equilibria, one thing you must remember is for pure solid and liquids, their activities are nearly equal to 1. Hence, when we write the Kc and Kp equilibrium, when it involves pure liquid and pure solid, it is just equal to 1. So, for example, in the first reversible reactions here, we have ammonium hydrogen sulfide, solid, decomposes to become hydrogen sulfide, and ammonia gas. So how do we write the Kc expressions of this? So basically, it's the concentrations of product hydrogen sulfide multiply with the concentrations of ammonia gas divided by the ammonium hydrogen sulfide here is solid, so the activity is 1, so basically it's divided by 1. And for the Kp expression, remember Kp expressions will only write for the gas. So in these reversible reactions, only the products hydrogen sulfide and ammonia are the gas. So we only include their partial pressure in the equilibrium constant expressions. So the Kp therefore is equal to the partial pressure of hydrogen sulfide multiplied with the partial pressure of ammonia. So now we move on to look at the second example. Water react with carbonate ion in the aqueous state to give hydroxide ion and also hydrogen carbonate ion. So for this, so how do we write the Kc expression? So the Kc expressions again is the ratio of product to reactant. So the product is hydroxide ion and also HCO3 minus ion. So divide with carbonate ion CO3 2 minus. For water, because it's pure liquid, so therefore the activity is 1. Can we write the Kp expressions for this reversible reaction? No, there's no Kp expressions for these reversible reactions. Why? Because do not involve gas. Reversible reactions and equilibrium could be reached in many ways. For example, in this reversible reaction, the system can start with only reactant present at the concentrations of 0.1 molar with no product. As the reactions proceed, the concentrations of reactant N2O4 decreases as the reactant is decomposed to become the product NO2. While the concentrations of product continue to increase until an equilibrium is reached when the concentrations of reactant N2O4 and the concentrations of product NO2 become constant. At equilibrium, the concentrations of N2O4, the reactant, is constant at 0.0000924 molar, while the concentrations of the product NO2 is constant at 0.09820 molar. To determine the equilibrium constant in terms of concentrations term Kc, the concentrations of the reactant N2O4 and NO2 at equilibrium are being substituted into the Kc expression, and the Kc value is determined to be 10.4. Or the system initially could have both reactant and product present. For example, in this reversible reaction, there is 1 molar of reactant N2O4 and 2 molar of product NO2. Then the system is left to react with the reactant N2O4 continues to decrease in concentration, while the product NO2 concentrations continue to increase until an equilibrium is reached. At equilibrium, the concentrations of reactant and product are constant. The N2O4 reactant at equilibrium, the concentration is constant at 0.5 molar, while the product NO2, the concentration is constant at 2.280 molar. To calculate the Kc, we just need to substitute the concentrations N2O4 reactant and NO2 product at equilibrium into the Kc expression. And the Kc value calculated is the same as the previous case because at both cases, the temperature is kept the same. For reversible reaction, we can also start with the product only. For example, in this reversible reaction, initially there is only 3 molar product NO2, but there is no reactant in the system. As the reactions proceed, so the product NO2 will combine to form the reactant N2O4. Hence, the concentrations of product will continue to decrease while the concentrations of reactant N2O4 will continue to increase until the equilibrium is reached. At equilibrium, the concentrations of NO2 product is at 2.498 molar, while the concentrations of reactant is constant at 0.6 molar. So to calculate the Kc, we just substitute the concentrations of the N2O4, the reactant, and the product NO2 at equilibrium into the Kc expressions. Again, same value of Kc will be obtained. Why? Because again, for this reaction, the temperature is kept the same as the previous one.